In the last segment, we talked about how to shield and detect radioactivity. In this segment, we're going to talk about writing balanced nuclear equations. Now, we've learned that equations must be balanced due to the law of conservation of matter, which means that matter is neither created nor destroyed. So if we have a nucleus and we chop off part of the nucleus, the two parts have to add up to the same mass and charge as what we had before. So we can write our nuclear equations. We can take the words that sound complicated and turn it into something simple. Radon-222 is an alpha emitter. So get out your periodic table and you'll see that it's element 86. Alpha emitter means it gives off an alpha particle. So it's really very straightforward. This number plus this number has to equal that number. This number plus this number has to equal that number. 218, 84. And then you're going to look at your periodic table and you see that element 84 is polonium. So you could write that as 218 polonium or polonium 218, or you could even write out polonium. Phosphorus 32 is a beta emitter. So we look on our periodic table and we see that phosphorus is element 15, 32, beta emitter, -1 and 0. So if you don't know the symbols and you don't know the charge and mass, you can't do these. So you need to know alpha, beta, and gamma. What is the degradation product? This number plus this number equals this number. This number plus this number equals that number. 32, 16. We look at our periodic table. Element 16 is sulfur. That's how we get sulfur 32 or sulfur 32. However it is that you want to write it. Okay? Iron 59. Iron is element 26. So you need your periodic table. If you don't have your periodic table, this makes this pretty hard to follow along. Beta emitter. What is the degradation product? Okay, so these are all renditions of the same thing, regardless of how you say it. 59, 27. 27 is element cobalt. And so this is how we get 59 cobalt or cobalt 59. Now sometimes we can get more than one particle, such as the next one where we have iodine 125 is an gamma and beta emitter. So iodine is 53 and we're going to give off a gamma particle. Huh? 125, 53, iodine. Isn't this the same as that? Well, yeah, it is. And so the notation is if you see the symbol little m, that means metastable. And that means that that iodine still has its gamma particle. So once it has given off its gamma particle, then we just say it's iodine 125, and now we give off the beta. 125, 54, look at your periodic table, that's xenon. Okay? If you don't like doing it in 2 steps, just do it in 1. 125, metastable iodine 53, gamma, beta, what do we have left? Some number plus 0 equals 125. Some number minus 1 plus 0 equals 53. 6 of one, half dozen of the other. Okay? Page 9. Okay, other properties of radioisotopes are what we call the half-life. Okay? And for many of you, if you came from Chem 110, and again, I'm sorry to keep going back to Chem 110, But many of you are here because you came from 110 as the prereq. And we don't talk about half-lives as being part of radioisotopes. But if we're talking about having radioactive waste, for example, we want to know how long it's going to be, quote-unquote, viable in the world around us. So the half-life is the time required for half of a sample to decay. So for example, carbon-14 has a half-life of about 6,000 years. How long would it take for 75% of an original sample to decay? Okay, so we want to do this the simplest way possible. We don't want to have to take the natural log and do a natural logarithmic decay. So we're going to go halvesies, so to speak. Okay, so let's say we start with 100% and we want 75% to decay, which means we have 25% remaining. 100%, 6,000 years later, we have 50% remaining. 6,000 more years, we have 25% remaining, which means 75% has decayed. So this would take about 12,000 years for 75% of an original sample to decay. By the way, I'm relaxing my sig fig rules here a little bit for emphasis. Okay, so we're going to say that's going to be about 12,000 years. Okay, now obviously if something's going to be around for 12,000 years, and actually it's around a whole lot longer than that, we don't want to use this as a radioactive tracer. It's around for thousands and thousands and thousands and thousands of years. So if we want to use a tracer that we would use medicinally, we would use something that has a much shorter half-life. For example, gold-198 is used for liver imaging and is a beta emitter. Its half-life is 2.7 days. If a patient received a dose of 0.3 rem, how many rem remain after 3 half-lives? Okay, so whether we care about what a rem is or not, it doesn't matter. It's a unit involved with radioactive decay, and we're just going to say, okay, I start with 0.3 rem. After 2.7 days, we have half of this remaining. Okay, so again, we're going to relax our sig fig rules. After 2.7 days, we're going to have half of this remaining. After 2.7 days, that's 3 half-lives. 1 half-life, 2 half-lives, 3 half-lives. 0.0375 rem is half of this. Okay? Or we could say 0.038, or if we want to round to one significant figure, 0.04 rem. In other words, we have about 1/10 of what we started with after 3 half-lives. Either of these are fine. Don't worry, on a test I'll tell you how many significant figures. Okay, now many of you are here because you want to go into nursing, and some of you will work with radioactive materials. So let's say that you were working with radioactive materials and you were accidentally exposed to P32 during a patient's treatment for leukemia. Its half-life is 14.3 days. Not terribly long. If the nurse still tests 15 picocurie, again, a CI is a curie, it doesn't really matter what the unit is, the process is the same as what we've done before. We're going to go back 6 weeks. Okay, so now 15 picocuries, 2 weeks prior, it's about 14 days, that would have been 30 picocuries. We're going to go back another 2 weeks, and that would be 60 picocuries. 6 weeks means we need to go back 2 more weeks, and that tells us the original exposure was 120 picocuries. In the next segment, we're going to talk about how half-lives can be useful for us.